So we're here on the second part of the 11.1 video and talking about the chi-square goodness of fit hypothesis test. We know that we have to check conditions for inference. The three conditions that we've been checking previously are random, normal, and independent. With chi-square, we are in a different probability distribution, so we're not looking for normal, not testing for normal. So we're going to be still looking for random and independent, but instead of normal, we want to make sure that our expected values, those are the ones that we calculated, are all at least 5. So when we check our conditions, it's going to be random, what we call large sample size, and independent. Random and independent are just as they were before, but large sample size, we're checking specifically for expected counts being at least 5. If we don't get expected counts of at least 5, we have an option to either combine two categories or more if necessary so that we do have expected values of at least 5, or we can still proceed knowing that our sample size really isn't large enough for us to be able to use inference. The format of the goodness of fit test is based on this template that you see. And so if the conditions are met, this is more or less the way we're going to format things. It's still going to be state, plan, do, conclude, our 4-step process. We're going to start with our hypotheses and the alpha that we're shooting for or testing against, and a definition of our population of interest and our parameter of interest. Then we're going to go through and check conditions. If conditions are met, we're going to state what test we're going to conduct. The do part is where we calculate the chi-square value. And there is a way that we can do it in the calculator. However, because usually the goodness of fit tests are over a small number, we're going to calculate these by hand. We'll use the calculator feature for the other types of tests, the homogeneity and the independence. The other part of the do is where we compare the p-value we get the p-value based on our chi-square, and we also list the degrees of freedom. The last part, of course, is a conclude, and that's where we talk about either rejecting or failing to reject based on whether or not we have enough evidence. Just a reminder that the chi-square test is based on the observed and expected counts. We're not going to do it with percentages or proportions at all. And again, when we're checking the large sample size condition, we're looking at the expected values. Those are the ones we calculate, not the ones in our sample. Those are the observed. If you need to calculate, and you're going to want to know more with more specificity what the p-value is, more than just between 0.05 and 0.10. And for that, you're going to need the calculator feature. So you're going to go to second vars for the distributions, and you're going to look for chi-square CDF. The format of the chi-square CDF, remember, it's reading from the right-hand side, so that's where our shaded area is going to be. And the way it's going to work is we're going to have chi-square CDF lower bound, comma, upper bound, comma, degrees of freedom. And then it's going to give you the p-value. So it's a right-hand probability. So our lower bound is always going to be our chi-square calculated value. Our upper bound is going to be some very large number, and our degrees of freedom, as we talked about before, is the number of values of the categorical variable minus 1. Next, we're going to take a look at an example that's actually, you can read it on page 686 in your textbook. And this is where we're looking to see if people are born evenly across the different days of the week. So go to page 686 in your textbook and read the example and then turn the video back on. So the null hypothesis, or I should say the research question is, do these data give significant evidence that local births are not equally likely on all days of the week? So that's kind of where our alternative hypothesis is. Our null hypothesis, remember, is going to be that we are saying it is even across the different days of the week. So our state, we wish to perform a test of, and then we are going to say what our null hypothesis is, that it's even across the 7 days of the week. The alternative hypothesis says that it's at least one of the proportions is not even, at least one of them is wrong, or it's not evenly distributed across the different days of the week. Remember that we can show it either in words or in symbols. And once again, I'm going to make a preference towards the symbols because it's going to help us later on in the problem. If an alpha is not given to us in the question, then we're going to use an alpha of 0.05. The next part is, of course, our plan, and if conditions are met, we will conduct a chi-square goodness of fit test. Be specific, because when they read the AP exam at the end of the year, they are looking to know that you know what kind of test you're supposed to be conducting. Then we check our conditions: random, large sample size, and independent. So the large sample size, we need to calculate our expected values. So we're going to add up all the births, and it's 140, and then take 1/7 of 140. So it's very conveniently 20, 20, 20, 20, etc. And those expected values are all at least 5, so we have met the condition for large sample size. Independent, we're using that 10% rule because we are sampling without replacement. Okay, the next part is the do, and this is where we expand the chi-square calculation, the summation symbol, and basically plug everything in and calculate the contributions to the chi-square test statistic by each of the different days of the week, the differences squared. So we don't know whether it's over or under unless we actually look at the raw data compared to the expected values, and we come up with a chi-square when we add them all together of 7.60. The next part, if you remember, is we need to state our degrees of freedom, and then we need to find our p-value. So our degrees of freedom is going to be 7 minus 1, or 6. We're going to go to degrees of freedom row 6, and then we're going to look for our chi-square test statistic. And we find that our p-value is 0.269. We had chosen an alpha of 0.05. So our p-value is larger, which means that we do not have enough evidence to reject the null hypothesis. So we fail to reject the null hypothesis and say that we do not have enough evidence to conclude that the births are not evenly distributed across the days of the week. So what this really means is, even though we can see they're not 20, 20, 20, etc., there are differences. It's not a significant enough difference to provide the evidence to disprove the null hypothesis and reject it. And the funny thing is, this doesn't really mean that our null hypothesis is correct. It just means that the sample that we got doesn't show a significant enough difference that this chi-square result couldn't have happened by chance alone. It could have happened by chance alone, which is why we can't reject the null hypothesis. So in fact, we saw, if you look back at the raw data, we have the number of births on the weekdays is significantly higher. Notice Friday, Saturday, and Sunday are the lowest days, and we know that the reason for that, and we've probably talked about this earlier in the year, is that sometimes births are scheduled, and that means that doctors don't like to work on the weekends or have people come in to have their scheduled births on a weekend. The next example that we're going to take a look at is on page 688 of your textbook, and it's all about the parent passing on specific genes. I think there's a problem about Gregor Mendel in our book. So pause the video right now and go read the question so that you have some background on this. Okay, so there's a specific proportion that we expect to see of the resulting plant offspring. So what they're going to do is run a chi-square test to determine whether or not the result of the offspring matches the colors that they predicted based on the theoretical probability. So first things first, of course, we're going to state, and you see it here both in symbols and in words, the biologist's predicted color distribution for the tobacco plant offspring is correct. And that means the probability of green, 0.25, the probability of yellow-green, 0.5, and the probability of albino of 0.25. And the alternative hypothesis is that it isn't correct, and we're going to use an alpha of 0.05. When we go to our plan, if conditions are met, we'll use a chi-square goodness of fit test. Random, they come from a random sample of the plants that were chosen. The large sample size, we calculate the expected counts, and you can see those in the column on the right hand side on the little table at the bottom of the screen. The expected counts are all larger than 5, and then independent, we use the 10% rule to check that. Next, we have the expansion of our chi-square test statistic. We end up with a chi-square axis value of 6.476, and that means that we have a p-value of 0.0392. So our conclude, and we ran this one in the calculator, obviously, with the degrees of freedom 2, because we had 3 different color possibilities, so 3 minus 1 is 2 degrees of freedom. And our p-value is smaller, so we reject the null hypothesis. We do have evidence that the biologist's hypothesis is incorrect. Remember that the follow-up analysis is that we want to be able to take a look at where the deviations come from. So the largest contributors to the chi-square test statistic value are going to be the ones that have the largest difference between observed and expected, and that could either be a positive difference or a negative difference. However, it's not just a raw difference, because we're dividing by the expected value for each of the different categories. It's going to be the biggest ratio of the squared difference over the expected. So keep that in mind when you're calculating, although sometimes we do calculate the first one, calculate the second one, and then ... calculate the last one. We can't do this follow-up analysis without calculating each and every contribution by hand, writing them out, and then having a clear look at which ones are the large contributors. So we have gone through all of our objectives. We saw a one-way table used to display the distribution of categorical variables. We calculated the expected values. We were able to conduct a chi-square goodness of fit test and make the claims, the null hypothesis, the alternative hypothesis. Let's see what else. And then we were able to determine degrees of freedom, as well as check the large sample size condition, check all the conditions, and then do the follow-up analysis with the largest components of the chi-square calculation. So in the next section, we're going to be taking a look at the 2 other tests of chi-square, homogeneity and independence. So I'll see you then.